So we're back. We have an ideal diesel cycle. This was invented by Rudolf Diesel in 1893. He put forward the idea, but by which we can attain higher thermal efficiency with a high compression ratio. Okay? High compression ratio. All diesel engine works on this cycle. Diesel is used as a fuel in this cycle as it can be compressed at a higher compression ratio. It is also called a constant pressure cycle. Okay, a constant pressure cycle or constant combustion cycle because heat is added to it at a constant pressure, and we have a high thermal efficiency with a corresponding compression ratio between 11 is to 1 to 22 is to 1 compared to O2 cycle that only have a 6 is to 1 and 12 is to 1. So we have a high compression ratio means high thermal efficiency. In this slide, we are able to see that the PV and TS diagram of the diesel cycle. So at first we have a top, no, I mean bottom dead center. Okay. So if we compress this one wherein the work has been applied, okay, isentropically, we have an isentropic compression and the volume 1 has been reduced to volume 2. But at the same time, the pressure has been increased from pressure 1 to pressure 2. So this is your status at 2. And if we look at the TS diagram, so this is the 1. We have the S1 and S2 since we are talking about isentropic compression. So the entropy from phase 1 to phase 2 are both equal. And that as we compress this 1 to 2, okay, the temperature has also increased and comes along with the pressure. Okay. Now, as the pressure or the air uh, up, achieve the pressure of 2, fuel is injected. Okay. The diesel fuel is injected. Uh, after the air is compressed. In this method also, we are able to eliminate the knock problem, which was discussed in the auto cycle that one of the problems in the auto cycle is the knocking. So as we inject the fuel, given the high temperature and a high pressure, there is a combustion. Okay. So meaning there's a combustion, there is a heat addition in this one. So given this one. So as the heat is added, the volume expands to a certain point, volume 3, this one. But also the temperature also expands or increases. However, the pressure 2 is equal to pressure 3. That is why we are calling it constant pressure heat addition. Okay? So this is the power stroke, the 3 to 4. It gives off power. Isentropic expansion. Okay. In the TS diagram, you have the work out here, but we have an isentropic expansion from 3. Entropy 3 is equal to entropy 4. And then we have the heat out, Q out. So constant volume heat rejection, whereby a volume 1 is equal to volume 4. So this one, but the entropy has been reduced from S4 to S1. In all, Otto cycle and diesel cycles are not externally reversible due to heat transfer through a finite temperature difference. Okay. Typically, and we have 11 is to, I said 11 is to 5, or 11.5 is to 1, or 11 is to 1, and 22 is to 1 are the ranges of the diesel compression ratio. Now, we want to determine the thermal efficiency. First, we have to analyze that what is coming in and coming out. And when we say thermal efficiency, it means the heat addition has been a part, or will always be a part of the solution. So we analyze this one, the thermal efficiency in the first law. So we analyze directly from the uh, constant pressure heat addition 2 to 3. Okay. So this means that we have the Q in. Of course, it is positive because it applies work over WB, or the work at the boundary out. Okay, is equals to the change of internal energy. Okay, we look at this one as U3 minus U2. Okay, of course, we have a bit of uh we'll say work has been done. So if there is a work has been done, at we see there's a change in volume from volume V2 to V3. So therefore you have an enthalpy. Okay, if you transfer that here, you have that okay, we will use that at U3 minus U2, and then we have plus P V3 minus V2. So this in all is a change of enthalpy with a constant pressure, and those we may take that as CP T3 minus T2. Okay, that's how it is, the heat addition. Now, if we take also a look at 4 to 1, the heat rejection, we have an outgoing heat. So this means that Q out minus work, okay, is equals to U4 minus U1. Now, we take note that volume 1 and volume 4 are equal. So that means it does not produce work. So we have to make this one a 0. Then, okay, Therefore, your Q out is equals to negative Q out is equals to U4 minus U1. Only the change of internal energy, okay? Because on the flip side, if we take a look at this one, this is the change of enthalpy if we have a change of volume. But if we do not change the volume, we have only an internal change of internal energy. Okay, see the difference in that. So therefore, the thermal efficiency of the diesel is, of course, we have the work net over the applied heat to make things running, which is also equal to, say, we just put it there, Q out over, no, I mean, sorry, okay, which is equal to mm, Q in minus Q out over Q in. Okay, so that makes it uh, 1 minus Q out over Q in. Okay, and if we substitute this one, the Q out first, so we have it's just equal to 1. Okay, how do you call this one? So take a note, this becomes CV T4 minus T1. Okay, and also this becomes, okay, if we rearrange the negative, if we put the negative and apply this one here, we have negative CV, and come to think of it, we have already interchanged the T1 and the T4. Now the T1 is uh, the first to be written because of the distribution of this negative value. T4 all over CP, which is the heat addition, T3 minus T2. Okay? And we have another introduction of variables in this one because there is what we call the cutoff ratio. The cutoff ratio uh, is just equals to V3 over V2. Okay, wherein the heat there's a cutoff of heat addition and fuel. Then before it expands and create work. So we have RC here, cutoff ratio is just equals to uh, volume 3, volume 2, or we may say a specific volume of air 3 over the specific volume of air 2, or the mixture or of the air. And we take note that we remember the ratio of CP over CV, which is just equals to K. So by this means that we just substitute this one, and after a lot of derivations, a lot of formations, which includes the RC, a compression ratio. So we now have the final form of your what's this thermal efficiency. So we have the R, K, minus 1, the compression ratio. We have also the inclusion of uh, cutoff ratio, RC, to the power of K, minus 1, all over this one. We have K here because of this CPCV. So this means 1 over K, and RC minus 1. Okay, we don't go along details of it. This is uh, a bit of tedious derivation. So this one, this value here is that when we take a look at this one, this should be always greater or equal to 1. Okay, there is a question here if the thermal efficiency of the diesel should be lesser than the thermal efficiency of the auto. But again, the compression ratio is being discussed here. Having a high compression ratio means that this one, or the subtrahend, okay, becomes lesser because of the greater compression ratio here. So 1 minus greater number becomes lesser. Okay, and if we took that away against a whole number 1 or 1, this becomes larger compared to uh, the thermal efficiency of the auto cycle. So I hope you enjoy the discussions, and thank you for your time and listening. So before we go out of this discussion, the advantages is it has a good reliability. This cycle has an outstanding power to weight ratio. The engine in which the auto cycle is used has a low cost, and also the working medium is also a low cost, and it has a high thermal efficiency. On the flip side, although diesel fuel used to be cheaper than gasoline, it now often costs the same amount or more. Although diesel fuel is considered to be more efficient because it converts heat into energy rather than sending the heat out the tailpipe as gas-powered cycles do, it doesn't result in a flashy high-speed performance. Uh, the diesel still needs regular maintenance to keep things running. You have to change the oil, the air oil, and the fuel filters. Finally, if you neglect the maintenance and the fuel injection system breaks down, you may have to pay a diesel mechanic more money to get things fixed than you would have to repair a gasoline system, because diesel engines are more technologically advanced. So, goodbye, everyone.